Hi, I'm Philip Bille. Welcome to this video on the quick union data structure. The quick union data structure consists of a forest of rooted tree. Each set corresponds to a tree, and the trees are represented by an array P of size n, such that the ith entry in P is the parent of element I. The parent of the root is the root itself, and the representative of the set is the root. So for instance, in this picture here, we have three sets represented as three trees. This set here is over here is encoded in the parent array by saying that element 1 points to 0, element 6 points to 0, and then the root, we let that point to itself, so element 0 points to element 0, and so on for the rest of the array. Okay, so how do we implement the operations? To implement init, we simply create n trees, each consisting of a single element, which is then all of them are then roots. To implement union, we first check if the input elements are from the same set by checking if they have the same representative. If they are not from the same set, we make the root of one tree the child of the root of the other tree. So for instance, if we look at this example here, we want to do a union 5.0, so that means that we want to union this tree with this tree. So we can make the root of, for instance, this tree the child of the root of this tree over here, right? So the child of the root, that means we should attach it to 0 here, as we do here. So we add this pointer here and then attach this this tree here to here. So we can freely choose which root becomes the child of the other root. But usually in exercises, we will specify some rule for deciding which one. Okay, so to implement the find operation, we simply follow the path to the root and then return the root, which is the representative. So for instance, if we want to do a find on, say, element 3 here, we say, okay, what's the parent of element 3? That's 2. What's the parent of 2? That's 7. What's the parent of 7? That's 7 itself, right? So this is the root, and so we return that. So let's see an example of the quick union data structure. So suppose we do init 9, that produces then 9 trees, each of which are their own roots. So if, let's see then, if we do union 3.2, so now we want to combine trees here containing 2 and the tree containing 3, and we can, for instance, do that by attaching the root of 3, which is 3 itself, to 2. So now let's do union 2.7. So now we want to combine this tree with this tiny tree over here. We can, for instance, do that like so. So now again we connect the root of this tree to the root of this tree. Another example. Let's see if we do union 5.4. So we combine trees 4 and trees 5. For instance, we can do that like so. So we get this tree. So now we're down to, let's see, 1, 2, 3, 4, 5, 6 trees in total. Okay, now we do union 8.3. So that means we want to combine this tree and then the tree containing 3. So that's this tree. And we can do that, for instance, like so, by connecting the root of this tree to the root of this tree. Another operation, union 1.0, so connect the two trees here, for instance, like so. Union 6.1, so now we want to connect this tree to this tree over here. So we, for instance, make the root of 6 the child of the root of this tree. Now we're down to only 3 trees. Union 7.3. So now we want to union this tree, this node, and this node. Well, these nodes are in the same tree, so nothing happens. Union 5.0. So now it's this tree that we need to combine with this tree over here. We can do that, for instance, by attaching the root of the tree containing 4 to make it a child of 0. Finally, union 6.2. So 6 is over here in this tree and 2 is over here in this tree. So we combine these 2 trees together, for instance, like so, by connecting the root of the left tree and making it a child of the root of the right tree. So that concludes our example of the quick union data structure. So quick union is straightforward to implement, and here is the full pseudocode. Again, you should spend some time to think about why this implements the operations we just described. We have that the init operation takes linear time. That's straightforward to see, just as before. And a unionified now takes order d time, where d is the depth of the tree. Why is this? Well, at a find operation, we start at some node, and then we traverse a path from that node to the root of the tree using constant time at each step. This path can be at most d long, where d is the depth, and hence the find operation takes order d time. The union operation, we start by doing 2 find operations. That takes order d time each. And then we change a single parent pointer using constant time. So in total, this operation also takes order d time. So how good is this running time? Well, it depends on the depth of the tree. If we are lucky, we might end up with a tree with a small depth, such as the one that we have over here. Here the depth is no more than 4, so this is always takes at most order 4 time to get from any node to the root. But in the worst case, we might end up with a tree like this that has linear depth. So the real challenge is, can we somehow combine the trees during the union operations to limit the depths of the trees that we get, so that we in that way get a better bound on the running time.